what this is telling you, it's telling you that you're really thinking of multi-pile NIM as 3 piles of single pile NIM and a directed sum. So that can be generalized, and we actually have a theorem now. So the theorem I just gave you for NIM sums for NIM actually generalizes for that weird idea of having several games sitting out in front. Each one of the games would be like a pile of NIM. So if GI is a Sprague-Grundy function of the capital GI, and the combined the sum of all those graphs has a Sprague-Grundy function defined by this thing, and this is the theorem, because the Sprague-Grundy function actually has a purpose. It's the max value of all the directed pieces of followers, right? So we have a definition of what we mean by followers. So you technically could calculate the SG function of the sum of a bunch of directed graphs. And it turns out that this SG function for the sum of directed graphs is just the SG function of all the little ones NIM summed. So you're NIM summing them. Just like you just did. You take the Sprague-Grundy function of the first vertex, just like you did when you did the directed graph, calculate that, change it to binary, take the second one, it could be from the second game, calculate the binary expansion, third one, calculate the binary expansion, add them all up, mod 2 by the digits, and that value that you get at the end is the value of the SG function for the combined sum of the graphs. That's the definition. Well, that's not the definition, that's the theorem. I'm going to prove it. So how do you prove something? I spend a lot of time in number theory showing how to prove something. But one of the things you want to do, the proof may seem like, duh, this would be what you should do. But it's not actually. You have to think. You have to prove it. When I say you have to prove it, I was thinking, who do I mean by you? Well, I mean you. Johnny has to prove this. So if I let B be that NIM sum, what do I have to show? Or what does Johnny have to show if you wanted to prove this? You want to prove this? No? You want to go to grad school in math. You want to prove things. Well, the Sprague-Grundy function has properties. The first one is that it satisfies this max property, right? That if there's a smaller number, a, an integer, and non-negative integer, that is smaller than this value, then one of the followers must have attained it. Remember, maxing is you take that set, and it's the smallest number that was not in that set. So that means that A is smaller than B. That means it has to be in the set already, because it couldn't be the max of the group of objects. So that comes from maxing. The second thing I have to show is that no follower has the max function equal to B, right? That it wasn't attained anywhere else. So really B was the smallest of all these things. Now in advanced calculus you have similar type of proofs where you have to show something is a limit or something is the sup or something is the inf. In those cases you have to write it out like this. What is it I have to show? I have to show it's the smallest, and I have to show that if there was something smaller, it can't be in the set. Those are you line it up like this, so it's very clear what you have to show. And in advanced calculus, that's really, really super important. Number theory, it's not so bad because some of the proofs are, at least the ones that we begin out with, are not as difficult. But the ones in advanced calculus, sometimes hard to sit there and figure out what it is you're trying to show. So if you can do an outline, like I have to show this first and this second, then it gives you these little mini pieces that you have to show. So these are the two things I'm going to show in pieces. I always try to break things up in pieces like this. So very soon in advanced calculus, how many of you are in that class? Because a lot of you are in that class. So if you're in advanced calculus, you'll soon have to show things like there's a limit. This sequence has a limit. And you have a good candidate for the limit because you kind of know what it should be. Maybe it's going to be the least upper bound. Maybe it's going to be, that's a great theorem to prove anyways. If you have an increasing sequence, it's going to be its least upper bound. So you already know what the answer is supposed to be. So what are you going to take? You're going to take your candidate for the limit and show number one that it actually is the limit because it satisfies that epsilon definition that you get from Dr. Mukherjee. And then that you can break up into pieces too. So you can do the same piece thing all over the place in advanced calculus. Maybe I'll have you guys do that in here in the beginning of class every time. Break up one of your proofs. Breaking up is not hard to do. Unless you're in love, then it's really hard. Okay, so how do I prove this? Well, I first start out, I took that little list that I wrote, say, what do I have to do? Well, I took a that's smaller than b. B is my nim sum of all those Grundy functions for each one of those things, which is defined because it has a directed graph, and I can get the g of x1, g of x2. I can actually calculate it just like you did in class. So I let b be that thing, and I choose an a that's an integer that's smaller than that b. And I'm going to let d be the nim sum of that a and that b. That seems like a weird thing to do. You're going to see where this works out. Well, if I have, when I nim sum things, I have to break things down to its binary expansion. So I'm going to take that d and binary expand that d. And the way I do that, if I did that the way I did with numbers, I would take the largest power of 2 that fed into that d, and that would be my leading term, right? So I'm going to do the same thing, but with symbols. There's k digits. I know there's got to be a 2 to the k exponent, and I know that that d had to be, did I have this wrong? It had to be of this form, right? The leading term will be 2 to the k. I think I have these switched around. Yeah, I have this correct. So 2 to the k was just a cap. A is less than b. Well, what does that mean if this a is less than b? And well, if a is less than b, then b must be the one with a 2 to the k digit. And a can't have a 2 to the k digit because it's smaller. But b is defined to be the nim sum of all these guys. So one of these g of xi's, because it's the nim sum, remember how we lined them up with the numbers? One of them has to have a 2 to the k term in it, or else you couldn't get the 1 into the 2 to the k piece, right? So I know that one of these guys has a 2 to the k term, and I'm going to rearrange these guys here so that that was the first one, the first component. I just rearrange my game. So let's say the second game had the 2 to the k term. I'll just make it the first game and rearrange them. Well, the direct sum, the nim sum of d and g1 of x1 has to be smaller than g1 of x1 because the 1 plus 1 is going to be 0 mod 2, right? So if they both have 1s in them and the 2 to the k term and I add them, that leading term will be wiped out. Correct? That's what somebody found here when they did the wrong problem. I forgot. Was it you guys? Yeah. Yeah, okay, so you found that. So Jenna's group found that if they actually put 47 instead of 37, or 37 instead of 47, you got a larger answer in the end. So there's no inequalities that hold. You have to kind of think like this. So there's a move from x1 to another vertex where that g1 of x1 prime has to be actually equal to this thing. Well, that's because of mexing, right? This thing was a mex function. So the only way that you can get this to happen means that there was something in there that you moved to that had that value. Well, that means that when I take that, if I take that vertex instead of the other vertex and I nim sum them up, well, that's the same thing as d nim summing g1 x1 all the way up to the end as well. And that's d nim summing b. But that's what I defined A to be, so that A is a move that has a G value. And that's what I wanted to show, that it was attaining a G value beforehand. So if A is smaller than B, then it must have been one of the followers' G value. So then, okay, that's the first part. I showed that if A is smaller than B, then A must have attained one of the G values as a follower. That's what that business was above. So now I want to show that no follower has a G value of B. So the way we do this is by contradiction. Assume that there was a follower that did have a G value of B. And assume without loss of generality it happened in the first game. So one of the games gave me a follower that gave me a G value of B. I'm just going to rearrange the games and put that game here first. Then B is equal to, I just put it here as the first one. The first one is the one that led to it. And that's defined to be this thing right here. But the definition of B is this thing right here, which is G of X. And that means G1 of X1 prime is equal to G1 of X1. But that fails the MEX function definition of G1. G1 is a MEX function. And the only way that you can, every time you got a MEX in your tree, it couldn't be equal to one of the followers. And now we just showed it was. So that's the contradiction. Messy proof. Good? What's the implication? What's the big deal? So you think, okay, I've got something scary here. I've got NIM, and I've got another game here, and I've got another game here, and I've got that these piles of games are like NIM piles. But so what? That seems very complex to put a pile of games and then start playing them all at the same time and say, oh, that's just like multi-pile NIM. Well, the reason this theorem is really important is it says that any impartial game, if you consider it as a sum of games, it's like a NIM pile. And we know everything about the NIM pile. That's Booton's stuff that I just showed you, right? We know a theorem about it. So the size of each pile would be the Sprague-Grundy function. So there's an equivalency between this set of games, or a game that can be broken up into a sum, and NIM, the multi-pile NIM. They're one and the same thing. So all of these games, all games are really multi-pile NIM. That's what it's saying. That's really what it's telling you. So your game with the corners, it doesn't fall under that scenario because it's not a combinatorial game. So you won't have this theorem at your fingertips, but you might be able to break it down. So what's the idea? The idea is to take a game that's really complex and break it down into a bunch of smaller games that can be directly summed. So multi-pile NIM is really single-pile NIM because they're really, you just have to focus on each of the piles separately. So that's what you want to do. See if you can take the game that you're interested in and break it up into smaller, easier games. So I'm going to leave this, let's see where we are right now. I'm going to leave this in-class assignment till next time and dwell on this. I'll post them up on YouTube. So it's not, this stuff is not easy either now. It's getting kind of more into some theory.